Electronegativity is probably the most important concept to understand in organic chemistry. We're going to use a definition that Linus Pauling gives in his book, The Nature of the Chemical Bond. So Linus Pauling says that electronegativity refers to the power of an atom in a molecule to attract electrons to itself. So if I look at a molecule, I'm going to compare two atoms in that molecule. I'm going to compare carbon to oxygen in terms of the electronegativity. And to do that, I need to look over here on the right at the organic periodic table, which shows the elements most commonly used in organic chemistry. And then in blue, it gives us the Pauling scale for electronegativity. So Linus Pauling actually calculated electronegativity values for the elements and put them into the table, and that allows us to compare different elements in terms of their electronegativities. For example, we are concerned with carbon, which has an electronegativity value of 2.5. And we're going to compare that to oxygen, which has an electronegativity value of 3.5. So oxygen is more electronegative than carbon. And the definition tells us that if oxygen is more electronegative, oxygen has a greater power to attract electrons to itself than carbon does. And so if you think about the electrons in the covalent bond between carbon and oxygen that are shared, they're shared unequally because oxygen is more electronegative. Oxygen is going to pull those electrons in red closer to itself. And since electrons are negatively charged, the oxygen is going to get a little bit more negative charge. And so it's going to have what we call a partial negative charge on it. So partial negative. Its partial sign is a lowercase Greek letter delta. And so the oxygen is partially negative. It's pulling the electrons in red closer to itself. Another way to show the movement of those electrons in red closer to the oxygen would be this funny arrow here. So the arrow points in the direction of the movement of the electrons in red. So carbon is losing some of those electrons in red. Carbon is losing a little bit of electron density. Carbon is losing a little bit of negative charge. So carbon used to be neutral, but since it's losing a little bit of negative charge, this carbon will end up being partially positive, like that. So the carbon is partially positive, and the oxygen is partially negative. That's a polarized situation, right? You have a little bit of negative charge on one side, a little bit of positive charge on the other side. So it's still a covalent bond, but it's a polarized covalent bond due to the differences in electronegativities between those two atoms. Let's do a few more examples here where we show the differences in electronegativity. So if we're thinking about a molecule that has two carbons in it, and I'm thinking about what happens to the electrons in red, well, for this example, each carbon has the same value for electronegativity, right? So the carbon on the left has a value of 2.5, the carbon on the right has a value of 2.5. That's a difference in electronegativity of 0, which means that the electrons in red aren't going to move towards one carbon or towards the other carbon. They're going to stay in the middle. They're going to be shared between those two atoms. So this is a covalent bond, and there's no polarity situation created here since there's no difference in electronegativity. So we call this a nonpolar covalent bond. All right, so this is a nonpolar covalent bond like that. Let's do another example. Let's compare carbon to hydrogen. So if I had a molecule and I have a bond between carbon and hydrogen, and I want to know what happens to the electrons in red between the carbon and the hydrogen, we've seen that carbon has an electronegativity value of 2.5, and we go up here to hydrogen, which has a value of 2.1, and so that's a difference of 0.4. So there is a difference in electronegativity between those two atoms, but it's a very small difference. And so most textbooks would consider the bond between carbon and hydrogen to still be a non-polar covalent bond. All right, let's go ahead and put in the example we did above, right, where we compared the electronegativities of carbon and oxygen, like that. When we looked up the values, we saw that carbon had an electronegativity value of 2.5, and oxygen had a value of 3.5 for a difference of 1. And that's enough to have a polar covalent bond, right? This is a polar covalent bond between the carbon and the oxygen. So when we think about the electrons in red are pulled closer to the oxygen, giving the oxygen a partial negative charge. And since electron density is moving away from the carbon gets a partial positive charge. And so we can see that if your difference in electronegativity is 1, it's considered to be a polar covalent bond. And if your difference in electronegativity is 0.4, that's considered to be a nonpolar covalent bond. So somewhere in between there must be the difference between nonpolar covalent bond and a polar covalent bond. And most textbooks will tell you approximately somewhere in the 0.5 range. So if the difference in electronegativity is greater than 0.5, you can go ahead and consider it to be mostly a polar covalent bond. If the difference in electronegativity is less than 0.5, we would consider that to be a nonpolar covalent bond. Now, I should point out that we're using the Pauling scale for electronegativity here, and there are several different scales for electronegativity. So these numbers are not absolute. These are more relative differences, and it's the relative difference in electronegativity that we care the most about. Let's do another example. Let's compare oxygen to hydrogen. So let's think about what happens to the electrons between oxygen and hydrogen. So the electrons in red here. All right, so we've already seen the electronegativity values for both of these atoms. Oxygen had a value of 3.5, and hydrogen had a value of 2.1. So that's an electronegativity difference of 1.4. So this is a polar covalent bond. Since oxygen is more electronegative than hydrogen, the electrons in red are going to move closer to the oxygen, so the oxygen is going to get a partial negative charge, and the hydrogen is going to get a partial positive charge like that.